Hello everyone, welcome back to another heat and mass video. So today we are starting homework for part B, and I have my paper here. I just have written our agenda for this video. So today we're going to be talking about a specific system where we have two different components that are mixed together as a liquid mixture, sitting in a Stefan tube, and then above that tube is going to pass some sort of vapor that's going to push for evaporation of the liquid and that like intermixing. So this is kind of a similar system that we had set up in a previous video, if you recall. But today we're going to have specifically, we're going to be given numbers so that we can actually see how the numbers are manipulated and transformed to give an actual output. And so for our system, we're going to have liquid acetone and liquid methanol as a mixture at the bottom of our tube. And then at the top, over the top of the lid, is going to pass vapor nitrogen. And then there's going to be some sort of rate of evaporation, sorry, of acetone and methanol due to the nitrogen kind of pressure change that we have. And then we're going to be using the Euler's equation to model how this evaporation is happening in Excel. So you'll be able to see how the numbers are changing depending on where we're at in the system. And then secondly, we're going to look at how scaling the Stefan-Maxwell equation can yield you a pretty good guess for what the fluxes of acetone and methanol are initially. So that's just also something that we're going to talk about in this video. But yeah, as you can see, I just have that initial agenda written there. And now we're going to start drawing our example problem. So we have our system, which I'm just going to model as like essentially a beaker looking thing. So we're going to have some sort of mixture down here at the bottom of both acetone and methanol. And these are both in the liquid phase. And then passing across the top of this system is going to be our nitrogen, which will be vapor. So we're going to label these with numbers so that we can refer to these through our variables, so we don't have to write, variable mass coefficient, mass diffusion coefficient D nitrogen. That's kind of really long to write, so we're just going to give them some sort of number value. So acetone we're going to have B1, methanol B2, and then nitrogen will be 3. So this is just what I have written here. This is our system. We have our liquid mixture, and then that line there, hopefully you can see that right above acetone, is going to be our interface between the vapor of the nitrogen coming down and the mixture of liquid evaporating up. That's where that interface will be. And then since, like I said, we're going to actually have some numerical values associated this time, the length of our tube between that interface line and the line where the nitrogen gas is being passed. So I drew these little dashes here just to represent some sort of thin, almost non-existing film there, just to say this is where our pure vapor is, and then in this area right here, we just have a nice mixture phase here where we have the vapor, acetone, and methanol, plus the vapor nitrogen kind of intermixing here. But that length is going to be 0.24 meters. And then we also have some sort of molar concentration percentage associated with the acetone and methanol and nitrogen. And since those are the three components in our system, all of those fractions will add up to 1 or 100%. So this is what I have written here, and I've just associated that distance as being delta. And then for the mole fraction, we're talking about the mole fraction when those three components are intermixing, so they're going to be gas, which means that they'll have the variable y for their mole fraction. So y of 1, which is, once again, our acetone, is going to be assigned a value of 0.319. Y2 will be 0.528. And once again, these are just going to be values that are given to us. I didn't come up with them using an equation or anything. They're just given to us for this equation, or for this example. And then Y3, like I said, is going to be 1 minus 0.319 minus 0.528 equals, let me get my calculator really quick. I don't feel like doing that in my head right now. Alright, and then that value will be 0.153. So once again, these are the mole fractions, mole percentages of how much acetone, methanol, and nitrogen we have in that mixture area. And then we also know that for the system as a whole, our pressure is going to be equal to 99.4 kPa. And then we also have an associated temperature. Our temperature will be 328.5 Kelvin. And so that's just going to be our temperature for the system as a whole. So I have those two values written down there. Okay, and so that's just including the pressure and the temperature of our system as a whole, and then that D that I had started writing over there. D is our mass diffusion coefficient. So these are values that we're going to have known. So you could Google, what's the mass diffusion with acetone in methanol? What is it for methanol in nitrogen? What is it for acetone in nitrogen? So we're going to need all three of those relationships here. So D12, which means the diffusion of acetone within methanol, is going to be 8.48 millimeters squared per second. And then our coefficient for methanol within, for acetone within nitrogen, so how acetone, which is 1, is going to diffuse within nitrogen, which is 3, is going to be D13 equals 13.72 millimeters squared per second. And then lastly, we need how methanol is going to diffuse within nitrogen, so we have all three of those relationships, and that'll be D23 equals 19.91 millimeters squared per second. So these are all relationships that we needed. These are all the numbers that we need to begin solving. So now that we have all these initial conditions set, all of these values, and then we know these, once again, this is an established relationship, we can begin solving for this equation. In order to begin solving this equation, we have to look at our Stefan-Maxwell relationships. So you will recall from an earlier video, we derived this equation and saw how it related to Fick's law. So you should remember this equation pretty well, but if not, we'll rewrite it right here. So Stefan-Maxwell relates to some sort of driving force. So that was denoted as D, the driving force of one component, seeing why this is diffusing, why it is making a phase change, evaporating, and that was looking at how the mole fraction of that component is changing due to some change in position. So that was kind of looking at, how is the mole fraction of, say, acetone different here versus at the very top of our system that we have, this dedicated area, or this dedicated volume that we have, how, depending on the position of how far away it is from that interface point to how close it is to the very end, how the concentration, the mole fraction of that is changing. And that relationship was established as the sum of all components in the system, and then seeing how the flux, the mole fraction of component I times the flux of component J minus the mole fraction of component J times the flux of component I divided by that total concentration of the entire system times how those two components specifically diffuse within each other. So this equation should look familiar. So you're going from, this sigma is supposed to be I is equal to 1 all the way until component J. So in our example here, we have I equals 1 until 3. So the first one would be component 1 times flux of 2 minus flux of, component 2 times flux of 1 over that total concentration times the diffusive coefficient of 1 in 2. So this is that Stefan-Maxwell equation that we've talked about many times before. So now we can just go ahead and write our Stefan-Maxwell equations for all of our components here. Excuse me. So we can look at what these equations are equal to if we're looking at acetone versus if we're looking at methanol, because that specifically is what we're trying to find the driving force of, as we defined in our beginning problem statement. We're trying to find the rate of evaporation of acetone in methanol. So we want to go ahead and define what the driving force is. So D of 1, or driving force of 1, which is acetone, is going to equal, so that's going to be our sum of 1 until 3. So you initially would start at 1, correct? So you do y1 n1 minus y1 n1 over concentration D 1 to 1. But you'll notice that that numerator will actually go to 0 and cancel out. So we're going to skip writing that relationship and just go to 2. So we'll have y1 n2 minus y2 n1 over our total concentration, which we will find in just a second, times that diffusive coefficient of 1 in 2. And then we have to continue adding on to that as we have a sum, right? And we're going to go till 3 because we have acetone, methanol, and nitrogen all in our system, and acetone was our defined 3 variable. So we'll do y1 n3 minus y3 n1 times the concentration times D13. So this is what the driving force will look like for our first variable, which is acetone. It's seeing how that is diffusing and changing within the methanol and then also within the nitrogen. So now we can write the same thing for D2, or the driving force of our methanol. We'll have y2 n1 minus y1 n2 all over total concentration D2 in 1. And you might be thinking, oh, we didn't define D2 in 1, we defined D1 in 2. But it actually doesn't matter, because that's going to be the same value no matter whether the acetone is diffusing within the methanol or the methanol is diffusing within the acetone. It will be the same value. And then we'll add, normally we would go to 2, but once again we'd have y2 n2 minus y2 n2, and that goes to 0, so we don't need to write that term. So we'll go ahead and go to 3, so we have y2 n3 minus y3 n2 over C D2 in 3. Okay. So now we have our two relationships that we've established for the driving force of both acetone and methanol, which is the same thing as that evaporation that we were looking for. So this is that relationship that we're going to have. And we can start to begin plugging in some numbers, but we don't quite have everything yet. So we're going to need to find the fluxes of these different components, and we're also going to need to find the total concentration. And our total concentration is actually going to be, so you'll recall the gas equation, PV equals nRT. So concentration is the same thing as finding the number of moles within a volume. So if we reformat that a little bit to be number of moles, so N over V, you will get P over RT. And like I said, N over V is the same thing as concentration. So we can just say that that total concentration is equal to the pressure of our system over our gas constant times the temperature of our system. And we know all of those values, so we can solve for that. Before we actually plug those values in, though, I also want to talk about another value in our system that's going to need to change a little bit. So in order for our equation to be easier to solve, we need to change that delta value a little bit. So we have that delta, which is the length between the interface and where we have pure nitrogen gas. So that mixture area, that gas mixture area, was equal to 0.24 meters. And we actually want to scale that to make it easier for us to plug into these equations so that it makes a little more sense. So we're going to define our scaling variable as being kind of a curvy n. So n is going to equal whatever position that we are currently at in that system. So kind of saying, oh, if we're, halfway through this, z equals 12.12 instead of some other value. So z is going to be like where we are in this volume that we have here, where we are going to be at in the y direction in that volume over the total length. So that's kind of saying it's essentially a percentage. So what percentage along are we? So if you are at the very beginning, you're going to do your position that you're at divided by the total that you have, and that gives you what percent along you are in that volume. And we're going to go ahead and take the derivative of this, so we get d of n equals dz over delta. That delta will not have a d in front of it, as it will not change, because that value is defined. And then we will rearrange this to get our dz, our change in position, is going to be equal to the change in our scaling factor times delta. So you'll probably see that we've defined this dz because we have to plug that into this equation here. So this dz can be plugged into this equation here. And now we can write this as a little bit more complicated expression. So we have that dy over dz is going to be the same as or equal to our dy, the scaling factor, that little curvy n, is equal to dy over dz times dz over d curly n. So this is just another relationship that we've formed, which will be important for plugging that back into our driving force equations from the Stefan Maxwell equation. So now we can see how this scaling factor is coming into play and why we've added this in here at all. So since we have this defined length, we can put this into our Stefan Maxwell equations and kind of simplify this a little bit. So we have the driving force of 1 and the driving force of 2 that we had defined above, but we can recall that the driving force of 1 is also equal to that changing, here, let me turn around, that changing composition over the dz, changing position, and we've defined that over here. So we can go ahead and write this in here. So we have dy1 over dz. It's going to be times dz over d curly n, or scaling factor. And then we have that as we wrote over here, has to be equal to our dn over our dz over dn, which we can see over here is actually equal to our delta. So we have that our delta is equal to dz over dn, and we have to write this equation relationship that we had defined over here to substitute in for this relationship here. And the dz's cancel out, so you're going to get, and also here, we have to add this entire expression that we've defined here, because we're saying that dy over dz, which is what we have written here, dy over dz, multiplied by the scaling factor relationship, has to also be multiplied to the other side. So all of this right here is going to be down here. I'm not going to rewrite it just for the sake of time, but I'm just going to leave that parentheses blank, and you'll recall that that is where we have that relationship of the mole fractions times the fluxes over total concentration and the diffusion coefficient. Excuse me. So now we can also substitute in that dy1 over dn, or scaling factor, is going to be equal to that dz over d curly n is once again equal to our delta. So that'll be equal to delta times the big old parentheses. So this is kind of how our Stefan-Maxwell equations have changed just a little bit to encompass this value here, that delta value. So with this, we can rewrite our Stefan-Maxwell equations that we had defined above. And this is when we're going to start getting into play for how scaling the Stefan-Maxwell equations can give us a pretty good guess for what the fluxes are to start for components 1 and 2, or acetone and methanol. And that's how we're going to begin using our Excel. So we don't know what these fluxes are, and there's not really quite a way to solve for it. So the whole reason why we did this rearranging with the scaling factor is so that we can simplify this equation as much as possible in order to make that guess for the flux. And then from there, we can take this guess and put it into Excel, and then use the solver tool that they have in Excel in order to actually solve for the flux. But we need some sort of initial value in there first, and that's why we've done all of this arranging here right now. So we have dy of 1 over that scaling factor, like I said, is equal to our delta times that big old parentheses, right? So we're going to begin simplifying this, and I'm going to distribute that delta into each of these terms. So we're going to write it as y1 times delta n2 over cd12 minus y2 delta n1 over cd12. So this is what I have written here right now. So all that I did is I pulled that y1 to the front of our fraction, distributed our delta in to the n2 all over the concentration and the d12, and then I just did the same thing for the second value right here. I pulled that y2 in front, distributed the delta, and then left the rest the same. So now we'll do the same thing for the second term right here. So now we have plus y1 delta n3 cd13 minus y3 delta N1 CD13. And the same thing can be written for our dy2, or how the composition of methanol is changing due to our change in scaling position. Sorry, I forgot to write N, by the way, sorry. So now that we have this, we can begin simplifying things here. So dy over d scaling factor 1, or n, is going to be essentially equal to 1. So you'll recall how I said that the scaling factor is essentially some sort of percentage of how far along we are in that volume, how far in the y direction we've traveled. So we're setting this essentially equal to 1 because we're saying that the composition over that scaling factor is going to be around equal to 1 with the ratio. So we can simplify this by saying it's around equal to 1. So I put that underneath that here. And then another term that we can look at, that we can simplify, is that third term over here. Oh my goodness. So I've just put that that's around equal to 1. And then here, see this N3, the flux of 3. That's saying that the flux of our nitrogen, cup is in the way, the flux of our nitrogen, if you'll recall from this example before, we had the acetone and methanol will diffuse upwards, but that nitrogen cannot diffuse downwards because it has nowhere to go. There's no volume here. The acetone and methanol can go up into all this free space, but nitrogen has nowhere to go down here. So nitrogen has some sort of contradictory flux that is reacting to the flux of the acetone and the methanol coming up, but it does not have a driving force necessarily going down a flux. So that entire term can be equal to 0 because we're simplifying that the flux of 3, or the flux of the nitrogen, is essentially 0 because it has nowhere to go. And then for all of these mole fractions, y1, y2, and y3, those are going to be essentially equivalent to 1. So those can be simplified out as of sorts. It's like you're just multiplying each of these fractions over here by 1. Okay? So hopefully that makes a little bit of sense. That's kind of how you can begin simplifying. And then we're gonna simplify this further in order to solve for this flux here. So now to solve for N2, so we can see that there's only one value here that has N2 in it. So we can say that this is going to be equal, so this value we can isolate and solve for N2. So if we rearrange it and say that N2, or flux of 2, is going to be equal to, and then that'll turn into concentration times our diffusive value of 1 and 2 over the delta, or that length. So we've just simplified this right here and solved it for the flux of 2, and this is how we're making our guess for flux of 2. Because this is the only value here that has N2, so we can solve for that. And you'll recall, as we defined above, that concentration is equal to the pressure over the gas constant and the temperature, so we can factor that back into here in order to make our initial guess. So concentration will be substituted in for pressure, D12 over RT delta. And now we can plug in general values for each of these things. So our pressure is around 100 kPa. We're going to round all of these values off so they're a lot easier to calculate because we're just making a guess. So we don't need things to be extra precise and particular here because we're just making an initial guess. We're just scaling it as defined in our second goal today was to see how scaling it can yield a good guess for the flux. That's what we're doing now here. So we have 100 kPa, which is times 10 to the third pascals. And then for our D12, we know that that is 8.48. But once again, we can round this off to 10, just because we are making a guess. And then this is going to be times 10 to the negative fifth, because this value is in millimeters squared, so we need to change this into meters. So times 10 to the negative fifth meters squared per second. And then down here, we have the RT delta. So R we know is 8 point, well, it's supposed to be 8.314, but once again, we're gonna round that off to 10 joules per mole Kelvin. And then T is 328.5 Kelvin, but we'll change that to 300 Kelvin just to make it easy. And then lastly, we have our delta, which is 0.24 meters, and we'll change that to 0.2 meters, just to, again, make it easy. So this is what we have down here. I plugged in our relationship that we found for concentration down here, and then rounded off all of these values and put them in the correct units so that we can simplify this and solve for a guesstimate of the flux. So we have this value equaling 1/600 here. So this is going to be our guess for the value of the flux of 2. But we're also going to establish this as the value for the guess of flux of 1. Because once again, this is a guess. We don't have to be super particular. We don't have to go through this whole equation all over again using the driving force of 2 and solving for 1. We don't need to do that. We can just extrapolate that to be also the value of the flux of 1, because they're going to be pretty similar. The diffusing factor for 1 and 2, and 1 and 3, and 2 and 3 is all very similar to each other. They're within a couple values. And then also our mole fractions are pretty similar too. They're not super far off. So we can just say that the flux of 1 and the flux of 2 are essentially initially 1/600. So now we can move on to Excel and start using all of this good information that we found in order to see how these values are actually changing and solve for the actual flux instead of this guesstimate. All right, so now we are at our Excel here. So I am going to begin plugging in all of these values that we had already defined initially that we're going to need in this Excel. So we have Y1, we're going to define as 0.319, Y2, 0.528, Y3, 0.153, and then we have pressure, make that capital P, 99.4 times 10 to the third, because, equals 99.4 times 10 to the third. Yes, oopsie. So this is in pascals instead of kPa, because we want to make sure our values are in all of the units that we want. Temperature is fine. And then we have R is equal to 8.314 here. All right. And then we can plug in all of our diffusion coefficients. Actually, I'll put C right under this, and we can go ahead and solve for our concentration. So like we defined before, C is that pressure divided by temperature times gas constant. So there's our value for our concentration. Then D12, or the diffusion coefficient between 1 and 2, 8.48, equals 8.48 times 10 keep putting the x symbol times 10 to the negative fifth, and then D13, 13.72 times 10 to the negative fifth. Okay, D23, 19.91 times 10 to the negative fifth. All right. Okay, so now we have our molar concentrations, pressure, temperature, concentration, total concentration, the diffusive coefficients for each of these, and then we also need our delta, which is going to be 0.24, and then, yes, so that's going to be total, and then our counter is going to be 1,000, so we're going to have 1,000 steps. So over here, we're going to have DZ, or whatever position we're in, starting at 0 and going all the way, where's our fill series? Starting at 0 and going all the way to 1,000 here, down the column. And then our position is going to be whatever this value is times our total. Oh, okay. So I messed that up. I need to do this guy here. Okay, and then at the very bottom, okay, I definitely messed that up. But at the very bottom, we should have 0.24, not 240. So let me go ahead and change that here. So our counter, definitely, so it has to be 0.24 divided by 1,000. Let's see if this works. Double check this. All right, yeah, final is 0.24. Perfect. So this is kind of saying what position we are at when we're going from that interface all the way up until where the vapor is pure over there. So now we can put our Y1, well actually we can put that down here. Y1, Y2, Y3, just so these values are easy to grab. So these are going to stay the same no matter what. No matter where, well, actually, sorry, these are the initial conditions that we have at that interface. These are the mole fractions. So we can see how this is going to change. I also need to add our flux gas over here. So we had 1 over 600 that we had defined before. And then we're also going to make all of these equations. So I'm pretty sure that's Control-Shift-2. Is that right? Nope, that is not right. Let me try it one more time. Okay, that still didn't work. Okay. Don't mind me, guys. Formula, create from selection. There we go. That's an easier way to do it if you don't know the shortcut, which obviously I do not. And then up here, we're going to have our dy1 divided by dn, and then, sorry. And then, once again, our dn is going to be equal to that change in position over our total delta. But this equation we had solved for and found what that was equal to. And we found that that was equal to that delta times what we had in those parentheses. So we can go ahead and start plugging this in. So we know that dy1 over dn is going to be equal to, all right, let me see if I can plug this in well. So we have y1, or actually, do y1 times parentheses, and then we have our delta times N2 divided by our total concentration, so C times C. Don't know why that's not pulling from this C here. Let me see if that works. Times D12. Okay, let me go ahead and put dots after these, because I don't think this is calling correctly. I think the rest of these were fine though. Alright, let's try that one more time. So once again, we have y1 times, and then on our numerator we have that delta times N2 dot divided by the C dot times our D12 dot, okay, and then we have that subtracted by y2 times, and then we had delta times N1 divided by C dot times D12 dot plus, and then that value, that N3 is not there anymore, so we just have minus y3 times delta times N1 divided by C dot times D13 dot. Alright, so this is what we have for our starting value here. Now we can move on to dy2 over dn. So this is going to be similar situation. So we will plug in the values that we have solved for. So it'll be slightly different because it'll obviously be for 2 instead. So we will have y2 times, and then in our numerator we have our delta times N1 divided by, and then we'll have our concentration times D21 dot this time, and then that'll be minus y1 times, did I accidentally, oh no, I'm okay. Why is this down here? What? Oh, I don't know why this is down here. This is supposed to be times N2. No, sorry. This is times D21, which is the same as 1, 2. Sorry. And then times F, times, in the numerator here, we're going to have delta, once again, times N2 this time, divided by the concentration times D21 again, or D12, same value, and then plus, nope, sorry, not plus, so once again, the N3 will be essentially equivalent to 0, so then we'll do minus y3 times delta times N2 divided by concentration times D23. All right, so this is what we have for our two values here. We can double check. We're doing Y1 times delta N2 C D12 minus Y2 delta N1 C12 minus Y3 delta N1 C13. So that should be good. And then this one we have, we should have Y2 times delta N1 C D12, which is the same as D21, minus Y1 delta N2 C D21 minus Y3 times N2 over C D23. Okay, so perfect. Now we have these two values, so that's great. So now we can begin pulling these values down. So this is going to be, so seeing how these concentrations are going to change as we go farther along. So it's going to be that derivative times our counter here. And then same thing for this, plus our derivative times our counter. And then here is just going to be equal to this, 1 minus this, minus this. So that's saying concentration of Y3 is just equal to 1, which is what the total has to be, minus the other two concentrations. So now we can pull all of these things down and make that go all the way to the bottom. All right, so let's see what we got here. So at the very bottom here, we have these concentrations not changing too drastically. So these values here we want to be equal to 0, because this is saying that at the very top, where it's just nitrogen passing over, there's this concentration of both methanol and acetone. And that's not correct, because at the top we're assuming that it's solely nitrogen, because that's where the nitrogen is passing over. So these values need to be equal to 0, and this value should be equal to 1, which says that the only concentration there is nitrogen vapor. So this is our value 1004 F. Okay. So up here we have F 1004, and then we have G 1004, and then we have H 1004. So this is the value of Y1 at our total length, which is delta. And then we have Y2 at our total length, which is delta, Y3 at delta. And so, like I said, we want this to be equal to 0, we want this to be equal to 0, and this to be equal to 1. So we know that our, do you recall how we said that the flux in the beginning was just a guess, and we actually had to use solver to find what it genuinely was? So this is where that comes into play. We know that these values need to be this, but with our guess right now, it's this. So we can use solver to rectify this. So what we're going to do is sum squared. So we're going to do the sum squared of this value here and this value. So this is what it is right now, but we want this to be as little as possible, as little as a sum squared value. So we will use solver here, we'll go to data, and then solver on the side. And so what we're trying to do is, once again, minimize this value here. So we're trying to minimize it, make it as small as possible. And once again, we're going to be changing this flux here. So that's like, those were our guess fluxes, but we want to find what the actual flux is by minimizing this sum squared here by saying that those two need to be 0, or as little as possible minimized in order to be more accurate to this actual equation. So now we're going to hit solve. And then this will begin solving for us. And it will change those fluxes on the side in order to make so here it's changed these fluxes to be what it actually is instead of what our guess was in order to make this as close to 0 as possible. So this should show us down here some pretty good results here. Yeah, we have this is essentially 0 and this is essentially 1, which is more actually world accurate. And then now we have our actual fluxes instead of what our guesstimate was. And that's going to essentially be everything for today. So I hope you enjoyed this video and that made sense for you. So thanks for watching.